In our next section, we're going to look at the Nexus 2K fabric extenders and specifically look at how to configure them to pair with the parent switches. And then we'll talk about what are some of the attributes in terms of the layer 2 versus layer 3 forwarding that they support, and also talk about what are the different types of supported topologies when we're using the fabric extenders to connect to either the 5K as the upstream switches or as the Nexus 7K as the upstream switches. Now, as I had briefly talked about before when we were talking about the hardware overview, what the Nexus 2K acts as is essentially a remote line card of either the 7K or the 5K chassis. Now, there are other parent switches that they can be paired with. They can be paired with the 9Ks and the 6Ks, but for our case, at least with these examples, we're mainly going to be focusing on them pairing with the 5Ks. Now, as we talked about previously, when we look at our traditional modular switch, like a Catalyst 6509, we have the supervisors that are controlling the control plane and the management plane. So that's where we console in or we telnet in, we SSH in order to make our configuration changes. And then when we apply configuration to the ports, ultimately those supervisors are downloading that config to the line cards in the control plane on the back end. Now, with the fabric extenders, we have the same exact type of design logic. The difference is that instead of the supervisors connecting to the line cards over the backplane of the physical chassis, we're connecting over the wires that we're connecting from the parent switch down to the fabric extenders uplinks. So in order to specifically support that, there was a new standardized protocol that was created that is commonly referred to as VN tag, where VN tag is essentially an additional header that goes on top of the Ethernet frame that tells the port extender or the fabric extender how to forward the frames as it's going between the interfaces. But with this protocol, one of the key points to remember is that the fabric extender is not an Ethernet switch. This means that it cannot make local decisions on how to switch traffic between the ports. Now, from a traffic flow point of view, what this means is that if we have two servers, let's say we have server A and we have server B that are connected to a fabric extender, let's say that this is a 2232 PP, and then upstream of the extender we have our parent switch, let's say that this is a 5548, and servers A and B, they're in the same VLAN, they're in VLAN 10. They want to locally switch traffic to each other, so host A sends a packet up to the fabric extender with the MAC address destination of B. If this was an Ethernet switch, the Ethernet switch would look at the CAM table and say, I know about the destination B, it's located on this local port, and then I'm simply going to move the packet to that destination port in order to get to the destination MAC address. But in the case of the fabric extenders, since they do not have a local MAC address table copy, they have to forward the traffic northbound to the parent switch. The parent switch then makes the decision and sends the traffic back down to the extender in order to actually switch the packet to the destination. So in other words, this means that from a traffic flow point of view or traffic patterns, if we're going from A to B, the traffic has to physically go up the cable that goes to the parent switch. Parent switch makes the decision, sends the traffic back down the same cable, and then it can go to the final destination. So this means that, again, in certain design situations, you may not want to employ fabric extenders if you have lots of east to west traffic patterns. Those type of services would be better connected to regular Ethernet switches that can make the local decisions based on the MAC addresses, whether we're connecting them at the top of the rack or whether we're connecting them at the end of the row. The main issue with the fabric extenders is going to be the oversubscription of the bandwidth that we're going from the port extender up to the parent switch. Now we'll see that from a physical connectivity point of view, there's a number of different ways that we can physically plug the servers into the extenders, and then how the extenders can talk upstream northbound to the parent switches. But before we get into all the details of what are the different topologies, what we're going to look at is the basic configuration of the extenders, how to turn them on, because it's going to take a couple minutes for the line cards actually to boot. And while they're booting, then we can talk about the details of the design options behind the scenes. So from a configuration point of view, the FEX config is pretty straightforward. We turn the feature on. So in the case of the Nexus 5K, we use the command feature FEX in global config. That's just turning the feature on. In the case of the 7K, we would install the feature set in the admin VDC. And then under the user VDC, we would say feature set FEX. That's going to turn it on globally. So one of the minor differences here that you'll notice between Nexus and Catalyst is that in Catalyst, if you want to enable LACP, you simply set the channel mode on the interface. Or if you want to enable OSPF routing, you just simply say router OSPF1. So all of the code features are enabled by default, or at least accessible by default. In the case of Nexus, you have to basically install the code packages to begin with by turning those features on. So in the case of our fabric extenders, that's going to be the first step, is that we're going to turn the feature on. Okay, specifically, if you take a look at the physical wiring diagram, and if you look at page number 2, we're going to be looking at the connectivity between 5K7, 5K8, and then our fabric extenders, which are 2K1 and 2K2, that go down to our converged network adapter, which is basically a 10 gig E NIC card that has 2 ports. One port is going to fabric extender 1, and another port is going to fabric extender 2. So first we're going to look at this from 5K7's perspective, talking to fabric extender 1, and then we'll talk about in a little bit more detail later why do we have this full mesh of physical connectivity from the extenders up to multiple parent switches. So what we're going to do next is on 5K7, in a global config, we're going to turn the feature on. So we say feature FEX, and once the feature is started, we're then going to look at the show FEX. Okay, what this basically tells us is that there are 2 fabric extenders physically plugged in to the parent switch, to 5K7, and this is going to be running through an automatic discovery protocol that we have enabled on the ports as soon as we turn the feature on. Now, what this does not tell us, though, is the details of how the fabric extenders are actually physically wired. It just says that we know somewhere that these devices are plugged in. Now, based on our physical wiring diagram, I know where these ports are physically located. They're on ports E110 and E111. But from this output, the only thing that we can really see is that we know what the models are that are plugged in, and then we know what the serial numbers of the remote line cards are. Okay, the next step is that once the feature is on, we're going to set the switch port mode to run as a fabric extender port. Now, what this ultimately means is that we're changing the frame format for anything that goes down that port to the extender in order for us to include the VN tag header onto the particular packet. What this is going to allow us to do is to signal downstream to the fabric extender what are the different ports that we want to send the packets between. And I don't remember offhand exactly what the spec number is for it, so let's go ahead and search for it. But it is it's an 802, or it's an IEEE standard that is called Bridgeport Extension 802.1BR. Okay, 802.1BR is the actual implementation of the VN tag protocol. And let me see, what I want to see is the 802.1BR frame format, which is this output here. Okay, what this is showing is that when a frame comes from the upstream parent switch and it goes down to the fabric extender, the parent switch is inserting this VN tag on top of the Ethernet frame. Basically, what this is doing is to tell the downstream extender what is the destination virtual interface ID and what is the source virtual interface ID. What this ultimately allows it to do is to make that decision of how we are going to move the packet from server A to server B based on the specific port numbers that they are located on. So in other words, when server A wants to reach B, let's assume that this is the first portion of their communication. So server A knows what the IP address destination of B is, but it doesn't know what the MAC address is. So in order to find that, it's going to send an ARP, an Address Resolution Protocol request. So A sends the ARP, and the ARP destination is broadcast. Now, from the fabric extender's point of view, it doesn't really care what the destination is. The only thing it really cares about is what is the source virtual interface. So let's say that the virtual interface here is Ethernet 1/1. This is going to get inserted into the VN tag and go to the upstream switch. Now, from the parent switch's point of view, we now know what the source MAC address of A is, and we know that they are associated on the downstream FEX port based on this source virtual interface. So in other words, the parent switch is going to say MAC address A is on port E11 of the FEX. Now, since the ARP request is a broadcast, it means that the frame is going to go back down, and the fabric extender is basically going to send it to all ports except the source VIF that it came from. So the broadcast goes that way, and B realizes that that ARP is for me. So it's going to reply, and it's going to say, send a unicast reply that the source MAC address is B, and the destination MAC address is A, because now it's a unicast layer 2 frame. When this comes back in to the fabric extender, the fabric extender is going to say now the source virtual interface is going to be E12, or whatever this physical port is that's plugged into the destination. It goes up to the parent switch. The parent switch says, well, now I know that MAC address B is located on port E12 of the FEX. And I also know whatever the tag value is that I'm assigning these to the virtual interfaces. So this means from the fabric extender's point of view, it doesn't directly need to learn what the source or destination MAC addresses are of the devices that are directly attached. The only thing it needs to do is to forward the traffic up to the parent switch. The parent switch does the MAC address learning on its behalf, and the fabric extender then only needs to do the switching based on the destination virtual interface address. And again, the point of this being is that the fabric extender on its own cannot switch traffic unless it is plugged into the parent switch. So if you were to physically cut off these cables that go from the 2K to the 5K, the 2K would start dropping all frames that are coming in from the southbound facing interfaces. It's essentially the same thing as unplugging a physical module from the modular switch. If it's disconnected from the physical backplane of the switch, it's not going to be able to send any packets. Even if you were to give the line card power on its own, if it doesn't have connectivity to the backplane, then it's not going to be able to do any actual switching. Okay, so next let's go to the, and actually I should have done this before because that's what would have caused it to boot, is let's go to that interface which is E110. If we take a look at the output here, E110, or the wiring is E110, and we're going to say that the switch port mode is a FEX fabric port. Okay, what this command is specifically doing is to say now all frames that come in that interface and go out that interface are going to have this VN tag associated with it. Now, as we had previously seen in the UCS class, this is the exact same thing of what the UCS is doing when we're specifying a port is a server port. So what we're saying is we go downstream southbound out of the fabric interconnect down to the I/O module of the chassis. We're going to include the VN tag format of the frame as it goes on top of the Ethernet. So then the I/O module can switch based on the destination virtual interface address, which is basically going to be the VNIC that is assigned to the actual blade. In our particular case here, the virtual interface is just going to be a port number that is physically attached to the fabric extender. Okay, so next let's look at the show FEX again. And what we should see here shortly, actually I need one more command here, which is on the port number, is I need to specify what is going to be the module number that we are assigning to the fabric extender. Okay, so switch port mode FEX here, this is what is turning VN tag on. FEX associate, this is giving it a line card number. So this is the same as physically plugging in your F1 module or your M1 module into slot number 1, 2, or 3. Depending on where you physically plug that card in, that's what the numbering is going to show up in the running configuration. So if you plug it into module 1, the numbering is going to be E11, E12. If you plug it into module 7, it's going to be E7/1, E7/2. Same exact thing here with the FEX associate number. So the associate number is going to be locally significant to the parent switch, and we'll specify that the FEX associate number we'll say is going to be 101. Okay, once we issue these two commands, in addition to globally we had said feature FEX, if we now look at the show FEX, we see that this particular box is now connected. If we look at the show FEX detail, we should now see that the line card powers on and it's going to go through its boot up process. Okay, it says the module is online, and eventually we should see that it starts to come up. Okay, post level is complete. Now, in addition to this, the parent switch automatically downloads the NXOS software from itself to the extender. So depending on what version the downstream FEX is running, it might take longer for it to do the boot up process because it might have to do a reinstall of the actual OS. Where in our particular case here, when we look at the show FEX detail output, it says that the local switch, so this is the 5Ks version, is 521 and 17. The FEX version is exactly the same, or in other words, we don't need to download the OS to them again. If we were to upgrade here even to another sub-release, let's say N18, then we would have to download this to the extender, and the extender is going to have to reboot in order to run the new image.